Activating groups are what we call ortho-para directors. Very little meta product is formed. Notice that 3%. That's not enough to write home about. Ortho and para, ortho being the predominant one, para being a minor product here. Meta, we're just not even going to say it is. Activating groups are ortho-para directors. So why? You may ask. That's a great question. Let's look at each of the options, the ortho attack, the meta attack, and the para attack, specifically focusing on the sigma complexes. Okay, notice how in both the ortho attack and the para attack, highlighted in green there is where the positive charge of the sigma complex gets right snugly up next to, that's right, the activating group, the electron donating group. In the meta attack, none of the sigma complexes are actually close to that CH3 group, the electron donating group. So meta sigma complex doesn't have anything super stabilizing. The ortho and the para, because their sigma complexes become more stabilized by putting the carbocation right next to our electron donating group, those decrease the energy of the sigma complex, make it more stable. The sigma complex obtained from the ortho and the para attack has a positive charge delocalized adjacent to the electron donating group, giving it a more stable sigma complex. And so those are the two intermediates that most likely form, the sigma complex from ortho and the sigma complex from para. So more ortho is formed just literally because there are two ortho positions and only one para, and so that makes more sense. The methoxy group, oxygens, right, specifically looking at anisole here, activates the ring 400 times more than just benzene. That's ridiculously more times. The methoxy group physically donates electron density via resonance, and so it is highly activating. Again, ortho-para directors. Methoxy group activates the ring so much, it is such a strong activator that it actually will catalyze, the Lewis acid catalyst is not necessary for halogenation because the ring is so strongly activated with that oxygen. Poly substitution is difficult to avoid. All right, so but what we see again is that we get positions that are ortho and para, O and P, no metas. Like the CH3 groups, the OCH3 groups are activating and still ortho-para directors, okay? Here the para is major, and that's just due to the ortho being slightly more sterically hindered, right? We got this methyl group before, we only had CH3s, okay? So it's just that extra step out. What you would need to know is that ortho and para are the only products that we get when we have an activating group on our benzene ring. And we see the same thing in the sigma complexes, right? Except for now what's even better is that we have one more extra resonance structure. More resonance, more stable, right? So when we're looking at those electron donating groups, the activating groups, we are stabilizing the ortho and the para sigma complexes, but not the meta. So meta we don't see. And there's the last just reaction coordinate diagram to prove it. Awesome. Nitro groups. Nitrobenzene is an example of a deactivating group. Both it's inductively electron withdrawing and was withdrawing because of resonance, which we just discussed. Nitrobenzene undergoes nitration 100,000 times slower. No, that's not a joke. That is actual. Nitrobenzene undergoes substitution reactions 100,000 times slower than benzene because it is pulling out so much of the electron density via induction and resonance that benzene as a nucleophile is practically non-existent. But when it does react, meta, 93% of the time. Ortho and para, not so much. Why? Let's look at the sigma complexes. For the same reasons as before, the carbocation gets put on the adjacent atom to the group, the electron withdrawing group now. So that electron withdrawing group getting that positive charge adjacent to it is so destabilizing that we do not see ortho or para. Right? We only want that carbocation adjacent to our substituent when it actually is a donating group, not a withdrawing group. So the electron withdrawing group deactivates the sigma complex formed from the ortho and the para attack. So we do see that the meta reaction coordinate diagram has a lower in energy sigma complex. Overall, electron donating groups are ortho-para directors. Electron withdrawing groups are meta directors, except there's always one exception, right? Halogens. When we have a halogen on our benzene ring, halogens withdraw electron density by induction because they are relatively large and polarizable and usually electron withdrawing, electronegative. They are technically deactivating. So that means that they slow the reaction down when they are already on benzene, but they can donate electrons via resonance. So their directing capabilities are ortho-para directors. So even though halogens make benzene slower at reacting, they still can resonate. So see the resonance there, yeah. Which means that by default, their sigma complexes for the ortho attack and the para attack are more stable. Let's look at some strong activators and some strong deactivators. Let's go through the whole list, okay? This chart is, I believe, in your textbook. It's just cut up here on these slides so that we can see them a little bit more clearly and larger. Strong activators, oxygens and nitrogens with lone pairs, all right? The only ones that are moderate are when those lone pairs could potentially have resonance in other sides of the structure like this. But notice that that oxygen could also go into the ring. Okay, so resonance is still a thing there. Weak activators, still ortho-para directing, right? All of the activators are ortho-para directing, are our alkyl groups. Primary, secondary, tertiary, etc. Strong deactivators, meta-directing, nitro, protonated amines or tetrasubstituted amines because of the positive charge, or carbons with 3 halogens. That is because of the ability of those halogens to make that carbon so electron deficient, delta positive. That would be something like a CBr3. If we put CBr3 there, right? If we brominated the benzylic position completely, that would make a strong deactivator, meta-directing. Moderate deactivators are our carbonyl groups or our nitrile groups. And then our weak deactivators, but ortho-para directing weak deactivators are our halogens. Remember, the halogens are only deactivating groups that are ortho-para directors. All other ortho-para directors have to be activators, right? And all other deactivating groups are meta directors. So they're right in the middle just to confuse everyone. Now, utilizing multiple substituents, when we think about already having 2 groups, what happens when we want to add a third? Now, the directing effect of all the substituents of the reactant will influence the regioselectivity of the reagents, okay? So the reagents tell us what we add. What are we adding? The directing substituents tell us where are we adding? Okay, so do not confuse those two. Because bromine is over the reaction arrow, that does not mean anything about its directing capabilities. We are adding bromine, but it's the methyl and the nitro group that tell us where we are putting that lovely bromine. Because methyl is an ortho-para director and because nitros are a meta director, that would be here or here. They're the same because of symmetry. So just pop it on one side. That is when the directing effects are nice, happy, hunky-dory, and they are working together. If the groups used to direct are different, and then the stronger one will dominate. Okay, so we have two ortho-para directors for our hydroxyl group. Ortho-para, let me just get some color matching here, would be here or here, right? Ortho and ortho to our hydroxyl group. The methyl group is also an ortho-para director, but ortho and para to that methyl group is here or here. Now, where are we going to put the nitro group? Well, because oxygen is a stronger ortho-para director, then we are going to follow it. All right, methyl can just go have a day by itself, okay? It doesn't get to participate. Now, steric hindrance must be considered when more than one product is possible, okay? So typically the para position dominates due to steric hindrance. The only time it really didn't was when we had toluene reacting, but typically for all of our other mono-substituted rings, the para position will be dominant. For 1,4 disubstituted rings, substitution will occur at the less sterically hindered site if more than one site is favored. All right. And for 1,3, for meta benzenes, when you're trying to put on a third substituent, just note that putting it right here is not going to happen, right? Not observed. Putting it on the position right in between on the number 2 position, right? You'll actually never get that product. Now, blocking groups. This is a synthetic style approach, right? This is going to be helpful when we start thinking about synthetic strategies. If you want to take this reactant and make this desired product, you can't just straight up do halogenation because para is the most predominant, right? You don't want to do that in a synthesis and just say, oh, I'll take the minor product, the ortho. No, you're going to use what we call a blocking group. You're going to install the blocking group, which would most likely install para. Then you're going to brominate so that the only other position is our ortho position, and then you're going to remove that blocking group so that it's empty. Yay, that's super fun. What's a good blocking group? Remember, sulfonation is reversible, so sulfonation is typically used as a blocking group. The synthesis can be accomplished just like this. We start with sulfonation and we'll add it on there. Right, there's our blocking group. Then we'll add our halogenation into the meta position to the sulfonyl group, but the ortho position to our tert-butyl group. And then we'll use dilute H2SO4 to remove that blocking group. That's what's great about sulfonation is it's reversible. It can go backwards. All right. These ones, always, always important to know. I love these spider diagrams. I think they're super helpful for concept mapping. Utilize it, keep the chart with you until you really, really hone in on all of the directing capabilities and the idea of synthetic strategies.